I'm very pleased to introduce to you Corey Maley. Corey is Associate Professor of Philosophy at the University of Kansas. He got his PhD at Princeton with Gil Harmon and Sarah Jane Leslie. Primary interests are computation, the nature of computation, the kinds of systems that can compute, and also the nature of emotions. He has a number of publications in both areas. The talk we're going to hear today on analog computation and representation is part of a forthcoming book with Oxford University Press called The Analog Brain. And so please join me in welcoming Corey.
Okay, thanks very much. Thanks for coming, and thank you to Mike for inviting us. Sarah and I, we've had a great time so far, and really we wish we could stay longer, but we feel lucky that we got here just before the coronavirus epidemic, so yeah, I'm glad we got to come at all. So I'm going to be talking to you, as Mike said, about analog computation and representation. This, by the way, this is a beautiful image of an analog computer from the 1970s. It's the Telefunken 770, I believe. It was a German analog computer. There's an artist in bigger London who has taken some really nice photos of some vintage computers, and this is one of them. So I'm lucky enough to have his permission to use his images, including for the cover of my book. So that's what that is. What I want to do before talking about this stuff specifically, I want to give a little bit more of general background to the kind of book project, and then just my research, even more generally than that, to kind of situate this stuff for a more general philosophical audience. So the general background here, one of my overall research projects, is I want to understand computation beyond just computability theory or Turing machines. And for better or worse, the philosophical discussion about computation is focused on a particular mathematical model of computation, which are Turing machines or computability theory. And of course, there's nothing wrong with studying this paradigm, and it's completely appropriate for certain kinds of questions, mathematical questions you might want to ask about what things are computable. But despite the formal rigor of the Turing machine paradigm, there are some things that I think we might want to look more generally at computation. And let me say what these kind of issues are. First of all, computability theory is not a theory of what kinds of things compute in the first place, right? So the analogy I like to make, which is kind of a silly analogy, is with, say, number theory, right? The mathematical theory of numbers. Once you've decided what kinds of things can be counted, then you can use the results of number theory to tell you things about what can be counted, right? So for example, sometimes it's very easy when it comes to what philosophers have called medium-sized dry goods, like apples and books. If you've decided that there are an odd number of them, then number theory can tell you, well, guess what? You can't divide them into two equinumerous sets, right? But number theory doesn't tell you what can be counted in the first place, right? So it's easy for some things, but for other things like maybe emotions or clouds, number theory is not going to tell you how to count those things or even what can be counted at all. Similarly, computability theory doesn't tell you what kinds of things are computers in the first place, right? The other thing is computability theory and the Turing machine paradigm is a formalization of a particularly limited type of human computation. So I'm not going to go into the details of what Turing machines are, but what Turing did was to say, let's look at what human computers, people computing mathematical problems, can do using just paper and pencil, following very, very simple rules, right? Turn that into a kind of mathematical model, and then you can answer mathematical questions by studying the mathematical model, right? But, human computers didn't just use pencil and paper, pencil and paper. They use other computational devices too. So if we want to understand the foundations of computation in a way that includes not just this very simplified version of what human computers did, I think we might be really eliminating ourselves by studying Turing machines only. So here's a nice picture that I found. This is a human computer at the NACA, which was the National Advisory Committee for Aeronautics. This is the predecessor of NASA. And she has her paper and pencil, right here, but she's also using a slide rule and an adding machine, right? Okay, so closely related to this last point, and the subject of the talk I'm giving today, is that analog computation has just been almost entirely forgotten. And it seems to be an entirely different kind of paradigm for computation than the symbolic or digital computation that we're all much more familiar with, right? And I think this is just interesting in its own right. If it truly is another kind of computation and you want to have a general philosophical account or understanding of computation, why leave out this separate kind, right? Even though there are historical reasons why analog computers were replaced by digital computers, it's not the case that we should all switch back to analog computers, but this is just a contingent fact, and I think we should understand these kind of computers too, right? But also, I think that this arguably might be a better account of the kind of computation that's relevant to cognitive science and neuroscience. Sometimes neuroscientists are sort of explicit about, they don't say it in these terms, but I think what they have in mind when they talk about the brain computing is actually analog computation. This is latent in a lot of the ideas that one can find in the literature. Okay, so here are just some examples. This is Christoph Koch. He's a very influential neuroscientist. And in his 1999 book, The Biophysics of Computation, the first line on the first page of the book is, "The brain computes," exclamation point, right? Another favorite example of mine, a few years later, Linda and Hauser, in a review article in the Annual Review of Neuroscience, first page, first line of their paper, they say brains compute. Not an exclamation point, they're much more sober. Those are particularly pithy examples that I like to use, because they're so succinct. But you can find examples all over the place, right? So here's just a random sample of papers I found from just the last couple of years. The neural computation of inconsistent choice behavior, high-degree neurons feed cortical computations, looking for the roots of cortical sensory computation in three-layered cortices, tracking the flow of hippocampal computation, pattern separation, pattern completion, and attractor dynamics, and so on. This is very easy to find, right? And the idea goes back quite a while. McCulloch and Pitts, arguably this is one of the first semi-explicit expositions of the idea that there's some tight relation between computation and what neurons are doing. They wrote about this decades ago. And also, John von Neumann explicitly kind of did a compare and contrast with one of his last publications in this book, The Computer and the Brain, from the 50s. All right, so much for background. Let me give you a brief outline of what's to come. So first, just to avoid some confusion, I'll just spend a couple of slides talking about what I'm not talking about. And then I want to illustrate some historical, actual analog computers. And the purpose of illustrating these is really twofold. The first is that we're just not all that familiar with analog computers, and the extent to which some people are, it's a very small subset of the analog computers that existed. And the other reason for doing this is to show that the kind of received view of what analog computation is about, namely that it's about continuity, is just not true. So then I'll argue for what it is that makes analog computers actually analog. And the short answer to that is analog computation involves manipulating analog representations. and then I'll tell you what that means. And then finally, I'll just mention some examples relevant to cognitive science and neuroscience. This is the part that I really, to be honest, know the least about. This is where I'm doing my most current research to figure out more concrete and better examples of where in the neuroscience and cognitive science literature this can be applied, or can probably be applied. Okay, so what I'm not talking about is computational simulation or mere simulation. So these are just some visualizations from different computer simulations from a variety of sciences. In case you're curious, and I know you are, this is the formation of a tornado. These are a couple of galaxies. Maybe they're black holes. They're spiraling around each other. This is some DNA being heated up and denaturing. And this is just a 3D visualization of the morphology of some neuron, right? So all kinds of sciences use computational simulations now. That is philosophically interesting. There are a lot of philosophical issues there for sure. And there are people doing work on this. You know, a lot of epistemological questions about these simulations get very, very complicated. What can we know about the phenomenon that we're studying given the complexity of these simulations, et cetera? But I'm not talking about just simulations. What I am talking about is computational explanation. And this is really due to Gualtiero Piccinini. He's a friend of mine, kind of a mentor of mine. He made this distinction in this 2007 paper where with computational simulations, what we're doing is just using the computer in some sense or another to model some phenomenon. But that does not mean that we're saying that the computational simulation of that phenomenon means that the phenomenon itself is explained in terms of the computation that it does, right? So when we simulate some galaxies spiraling, we're not saying that we are explaining what the galaxies do because the galaxies are computing something or other, right? But in a computational explanation of some phenomenon, which is what we find in neuroscience and computer science, we're saying that we can explain what the thing is or does by appealing to the computations that the thing literally performs, right? And this is the kind of thing, you know, when people like Christoph Koch and other neuroscientists say the brain computes, this is what they have in mind. They're thinking, well, you know, we can explain what the brain's doing by discovering what computations the brain literally performs, right? Now, not all neuroscientists make this kind of distinction. Some neuroscientists are just interested in simulation. But the point is we can make this distinction, and I'm talking about the computational explanations, not just simulations, right? So that's what I'm not talking about, and what I am talking about. Okay, so let's talk about analog computers now. Like I said, the reason for doing this is twofold, because they're just not very well understood, and I'll start with a nice quotation from the special issue of the IEEE Annals of the History of Computing. The author here in this introduction to the special issue says, because digital computers and computation have been so successful, they've influenced how we think about both computers as machines and computation as a process. So much so, it's difficult today to reconstruct what analog computing was all about, right? And this is very true. And I'm just using those quotations because, you know, these people say these things in a way that's better than what I could come up with myself. So the received view of analog computation, again, due to my friend Gualtiero Piccinini in his recent book, he says analog computation is often contrasted with digital computation, although it's a vaguer and more slippery concept. Roughly, analog computers are systems whose function is to manipulate continuous variables. Variables that can vary continuously over time and take any real values within certain intervals, specified by differential equations so as to instantiate appropriate functional relationships between the variables. Insofar as people think about analog computation today, this is more or less what they think. It's basically just about continuity, right? So more succinctly, we can say Analog computation essentially uses continuous, as opposed to discrete or digital, variables to represent or model or approximate continuous problems of interest, right? This just is the kind of received view. This is what everybody thinks. I'm going to show you why that's wrong pretty soon, but let's go through some types of actual analog computers. In general, there were three types. There were mechanical, electronic, and electromechanical. I'll go through some of each type. So first, and by the way, in writing this book, this is a kind of thing where I really wish I could include videos in the book, because this one in particular is very difficult to describe in words and just diagrams. The animation is extremely helpful. So this is a mechanical multiplier, and this video is taken from a set of training videos that the Navy produced in the 1950s, just showing how the various individual components of mechanical analog computers worked. So here's how this works. We'll kind of take it apart and look at it component by component. What we have, I mean, it's already obvious what's going on, right? Not really. We have two inputs. We have A and B here, and then this shaft is the output shaft. So we'll look at just A. A can slide up and down, and then there's this linkage here, and there's a fixed pin right there. So as A moves up and down, it moves this linkage, right? That pin doesn't move. Now B moves left and right, and there's a sliding pin here, so that when B moves to the left and right, or as A moves up and down, that sliding pin moves its position, right? So as B moves to the right, sliding pin goes up there, right? So far, so good. Now, the sliding pin drives the output, okay? So as A moves, it drives the sliding pin there. As B moves, it drives the sliding pin, which drives the output, right? When the two pins are on top of each other, basically, that's the sort of 0 point, which will make sense in just a second. How does this thing multiply? Well, if we add values to A and B, where we start with 0, positive numbers, negative numbers, and then positive and negative, we can see as we move the inputs, the output just is the product of the two inputs. So if A is 2 and B is 3, the output is 6, right? I'm assuming everyone knows how multiplication works generally. So 4 times 4, we have 16, right? And then if we move an input to 0 on either side, doesn't matter what we do with the other input, it's going to stay at 0 as you'd want, right? Same thing on this side, right? If A is 0, doesn't matter what we do here, it's 0. And then it also works for negative values too, just as you'd expect. I think we get one more example of that. So when A is -3 and B is +4, we have -12 over here, right? So a mechanical multiplier, like I said, once you see how the pieces move around, it's fairly easy to understand. But in words, this is a nightmare to get anyone to understand. Okay, so a sort of complex mechanism to do a fairly simple mathematical operation. The next example is the opposite. It's a more simple mechanism to do a more complex mathematical operation. So the next example is a mechanical integrator. So just to refresh your memory about what integration is, if we have this function, the black line, and we want to integrate it, what we really want to do is calculate the area under the curve, right? And in a sense, it's a kind of running total of the sort of sum of that area, right? So one way to do this with a mechanical analog computer is with what's called a ball and disk integrator. So because this is the Navy, they're going to use some labels that don't particularly matter for us. But what the mechanism is here, we have a turntable that's going to rotate at a constant speed once we start the mechanism, okay? And then there are two ball bearings here that connect it to this roller up here. The input is this thing here, which is going to slide back and forth so that these ball bearings, or that bottom one, makes contact at different points along the turntable, right? Once the turntable starts, these things spin, which makes this roller spin. And if it's right at the center, the ball bearings aren't going to move, so the roller is not going to move. As it gets further out toward the edge, the roller is going to move faster, right? So what happens is, go ahead and play it. Yeah, so this is time, or your independent variable. Range rate is what they're calling the function. This basically just follows that black line, right? And then rate change, this is the output. This is going to be the definite integral up to a certain point in time. So we start the machine, and this is constant. As they're out to the edge, this is rolling faster, right? And as we count the number of rotations of this thing, that just is the definite integral up to that point in time, right? So then it's in the middle, so it's 0, goes back out, goes faster, and then really cool, when it's negative, it goes over here, it doesn't show that, but then it spins it the other way, which is what you want for an integral, right? And then this, of course, you can put a lot of these together. This could be the input for another component. Put a lot of those together, and you get what was called the differential analyzer, which was the first kind of large-scale, in a sense, general-purpose mechanical analog computer devised by Vannevar Bush back in 1931 at MIT. Vannevar Bush is a huge figure in the history of science. He went on to found what became the NSF. Prodigy, fascinating figure. One interesting fact about him is that his first name rhymes with achiever, not Vannevar. So now you'll know that if you don't remember anything else. But these different wheels and things were a lot of what I just showed you put together in more complicated ways. There are a lot of engineering challenges to get these things to work in the right way. And that's a fascinating topic, but it's kind of beside the point of this talk. Okay, so those were both examples of mechanical analog computers. Let's talk about some electronic ones, and specifically the one that we're most familiar with. If you know anything about analog computers in general, this is what people tend to know about, which is the analog differential analyzer. So let me start off with the kind of problem you would use an electronic differential analyzer to solve. This actually comes from a textbook, a 60s era textbook on analog computing. So this is a spring mass problem of the kind you'd see in a differential equations class in physics, where you've got a mass here and it's connected to this wall over here by a spring that has kind of a spring constant. And there's some friction on the floor. That's B right here, the spring constant's K. And, as you always want to know, like what happens when you push the mass, Well, it's, your intuition is it's going to oscillate a little bit, right? But because there's actually friction there, it's going to slow down and stop, right? How quickly that takes is going to depend on the spring constant and the coefficient of friction there, right? But some physics, and you can just turn this into a differential equation with some initial conditions, right? And the details don't matter a lot for us here, but these are some particular values that they use. And so once you have this system here, or this equation with the initial conditions, now you could just solve this analytically. You don't need a computer to solve this, but it's a textbook example, so that's what we're going to do. Once you have this mathematical characterization, then you just turn it into an electronic circuit. And so this is the kind of analog computer that most people know about. Again, the details don't matter a lot for us here, but we have a component that sums all of its inputs, that feeds into an integrator, that then feeds back into an inverter multiplied by 3. There's our 3. Goes back to the sum here. So there's one feedback loop, a second feedback loop, and you can see the constants, negative 80, negative 0.46, and 2. So you start this thing by basically applying the right voltages. The output is here. You watch what happens to the output over time, and lo and behold, it oscillates a little bit and then goes back to where it would start, right? So that's the kind of thing that most people are familiar with electronic analog computers. Put a bunch of those things together and you get the image that I started off with, that first slide. And this is a kind of closer view of that same computer. And you can actually see this is an engineer doing some tests on this, and she's you can kind of see she's actually testing an example very similar to the one I just showed you, right? I don't think this is the output, but maybe it is. So those were electronic analog computers, right? Okay, so far, none of these examples really challenged the idea that analog computation was just about continuous stuff in some sense or another, right? So now is where I show you the lesser known examples where that's not the complete story. And I found another great quotation in this other analog computing textbook where the author says, 99 and 44/100ths% of the time, when an engineer speaks of an analog computer, he's referring to an electronic differential analyzer, the kind we just looked at, or an EDA. But the EDA is just one type of analog computer, one specific application of the general principle of computation by analogy. So let's see, first of all, what is meant by analogy and how we use analogs in computation in the general sense, not just in the EDA. So let me show you a few examples of these things that were just on the side of purely electronic analog computers. These are just some simple circuits that were used to implement various kind of discontinuities. So we have an absolute value function, right, which is going to be non-negative everywhere. Here's a zero limiting function that's just going to be, non-negative. It's going to be 0 for negative inputs and then just linear positive for positive inputs. There's a bunch more of these for various kinds of engineering problems, like this is called a soft limiter. This, for some reason, is called a bang bang. There are a bunch of these, right? That's kind of interesting. What's more interesting is what you can do when you put these things together. So let me again motivate that by a particular kind of problem. The system we just looked at, we were able to, it's a textbook example. We could just say, look, we can analyze this into a differential equation with initial conditions. From that, we build our circuit, right? But what happens when there is no mathematical characterization? What we have is a curve, and we don't know how to characterize this mathematically. Now, let me hold off one thought you might have, which is, well, there's lots of ways of approximating known functions like this, right? Yeah, I know, we'll get to that. But one thing you could do if you didn't want to go through all the hassle of that is, well, here's a quotation about it. Such behavior presents almost insurmountable obstacles to purely mathematical investigation, but poses no particular difficulty to analog computer investigation. Again, we're not solving equations, we're modeling systems. Thus, if we can just describe the input-output relationship, all we need to do is provide an element on the computer which has the same relationship between its input and output voltages, because everything was in voltages here. Such elements are known as arbitrary function generators. So, kind of a mouthful, but the basic idea is, you've got this arbitrary function, we don't know the mathematical characterization of it. The simplest way to approximate this is just with a piecewise linear function, right? And so often that's what they would do. Just use an arbitrary function generator. You plug in various points, and different arbitrary function generators would have, different numbers of points that you could use depending on how complicated your function was. And then you can have this discrete approximation to an arbitrary function, right? Okay. Mathematically speaking, these are actually still continuous functions. So if you want to be really nitpicky, you can say, well, wait a minute, that's still continuous. Yeah, they have parts where they're not differentiable. You can call those discontinuities if you want, but really it's still continuous, right? They're still all connected. So let me show you an example of a truly discontinuous analog computer element, where what we want to implement is a step function. Right, this is just, there are lots of other examples. This is the sort of simplest one to understand, where we have a function that, it's just a flat value, and then it jumps with a discontinuity to different values, right? So one way this was implemented is with an electromechanical component, which was called an electromechanical step function generator, right? So electromechanical because it's a mechanical component, but what's at play here are still voltages, but the voltages aren't being manipulated electronically. they're being manipulated mechanically. So the way that this one works, I'll show you an animation that took me forever to make, but I'll explain it first. We have a resistor here, and we have different contact points on the resistor. And this is a dial that's going to rotate counterclockwise. Oops. So as it rotates, it's making contact here, then it's going to break contact, make contact here, break contact, and then make contact with the wire that goes down to here, make contact, make contact. So depending on where you put the various contact points and how you connect them, and how quickly you move that dial, you can generate a true step function electromechanically. So this is what it would look like. So there's the output as it makes contact with different points on the resistor, right? So just one more time. So just moving these parts around, the way the components were made, that was, parameters you could set. You could have, any step function you wanted, right? So a truly discrete, but yet analog computer, right? And these things were not, it's not like these were things no one knew about back in the 40s and 50s and 60s. These are in all kinds of analog textbooks. It's just we don't use analog computers anymore. So everyone forgot about this, right? So quick little note here, if you have a step function, why don't you just approximate it with some continuous components, because we can do that, right? So the most familiar way to approximate a very simple step function like this is just to use like kind of a Fourier series, right? You can do that, but another nice quotation, for the problem being studied, you might think it's not immediately obvious why the relay, that electromechanical component I showed you, is necessary. Because the voltage can be made to closely approximate a step function, right? We can use continuous components and closely approximate it. But there are reasons why this isn't practical. The slope of the step function out of that circuit isn't exactly 0 after the original discontinuity. And in the process of adding, say, 2 of those step functions, a small error that increases with time would be applied to like an integrator down the road, right, downstream, and cause unwanted drift. Basically, you're introducing errors when you don't need to, right? If you want to implement a step function, implement a true step function. You don't need to do it continuously, right? Okay, so back to the received view. The analog computation essentially uses continuous as opposed to discrete or digital variables to represent or model or approximate continuous problems of interest. Well, it's just, historically, that's just not true, right? Do your homework, look through the old analog textbooks, and it's just not the case. So this is what I think is the better view, which at first sounds circular. Analog computation is computation that involves analog representation. So now I owe you a story of what analog representation is. So according to me and David Lewis, analog representation is representation in which the quantity that's being represented varies monotonically with the physical property doing the representation. That's sort of a mouthful. It's easier to see in pictures. So here we have what I take to be 3 uncontroversial examples of analog just representations, simpler than computations now, right? So an analog thermometer, how does this work? These used to be filled with mercury, now they're usually dyed alcohol. As the temperature goes up, literally the level of the liquid inside goes up, right? Monotonic covariation, just as one goes up, the other goes up. Vinyl records, slightly more complicated when you have stereo records, but the same idea. Focus on just like, say it's just not a stereo record, just a old school monotone or monotonic recording. As the sound amplitude increases, the sound gets louder, the little grooves also increase in frequency, right? Or increase in amplitude. As the frequency of sound represented increases, the frequency increases, right? That's why you can take records and you can take a needle and a cone of paper, right? And tape it, and you can spin the record, and you can play it with just your little simple mechanism, right? The second hand of an analog clock, right, as the angle increases, so does the amount of time that's passed, right? And the important point here is, I mean, the analog clock is the best example. That's true, that's true whether this literally sweeps in a continuous fashion or if it goes in discrete steps, right? Or if it's a digital display where it goes in discrete steps. So it's, you know, in a physical clock, you might say, well, wait a minute, it might tick in discrete steps, but it's really moving continuously that whole time. Under my account, that stuff doesn't matter. What matters is the covariation between the physical stuff that's doing the representing and what it represents, right? So to contrast this with digital representation, just to make the point really clear, you know, here's a thermometer representing 25 degrees. Here's one representing 90 degrees. That one literally is taller than this one, right? Physically, it's taller. Here's a digital representation of the number 25. Here's a digital representation of the number 90, right, in base 10. What this represents is smaller than this, what this represents, but, you know, it's the same font. This isn't actually bigger than this is, right? They're just different symbols, right? That to me is the key difference between analog and digital representation, right? So, last part of the talk here, what does this have to do with brains? Well, this is slightly hand-wavy. Like I said, this is the part that I'm working on now. But like I said, I think there are a lot of places in neuroscience where this is already what neuroscientists are talking about. So let's start with, you know, the kind of dogma about the way that neural spikes work. McCulloch and Pitts start off their paper saying, you know, because of the all or none character of nervous activity, neural events and the relations among them can be treated by means of propositional logic. We don't really think of them in terms of propositional logic anymore, but we do think they're basically all or none events, right? So, you know, here's a kind of made up recording of some neural activity, and we often say, okay, well, yeah, you know, there's a spike, there's a spike, there's a spike, there's a spike. And the general view is, you know, the actual shape here doesn't really matter, right? It's just whether there is a spike or not, right? So in the simplest of neural codes, here's a nice cartoon of Adrian doing his experiments, right? We have a kind of a rate code here where the more mass we put on this muscle, the greater the firing frequency of the neuron, right? Well, if we think that these things are discrete events, this is a really simple example of an analog representation, even though the things are discrete, right? Stimulus increases, what's being represented increases, and so does the frequency, and it doesn't matter that they're discrete events, right? It's just a straightforward analog representation. A more complicating thing is that there's some recent research that actually, at least in some parts of the brains of some organisms, the waveform of individual neural spikes does matter. It makes a notice or a significant effect, has a significant effect on postsynaptic neurons. So if the spike is, you know, a little bit taller, that has an effect. If the spike is a little bit wider, that has an effect. I'm not an expert in this, but from what I understand in talking to some of the neuroscientists who've done this research, this is largely the result of just better experimental apparatus to be able to measure these kinds of changes. So it's not like people were being sloppy in the past, it's just that we weren't able to measure these kinds of small but significant effects. So these are two of the people. Dominique Deban is one of the people that's doing a lot of this research. The name for this has been called analog digital modulation of synaptic transmission. It's not really what I would love to call it, but that's what they call it, so whatever. But, you know, they've been arguing that in all these places, the action potential is not what they call a digital event, right? It actually is, there is some information in that waveform. So that's another area where there is an avenue for, you know, us to kind of get our analog foot in the door for what's actually going on. when brains compute, or we can take literally the idea that brains compute, right, but not digitally. They might be analog computers, right? And this is kind of just a picture from one of their results. It's kind of incomplete, but the idea is, as the axonal spike decreases, there's significant differences in the postsynaptic response in the current, right? Higher level stuff, classic results from Shepard and Metzler have to do with analog mental rotation, right? If you've not seen this before, it's a really cool result. What they did is give participants pairs of 3D shapes, and participants were told, okay, as quickly and accurately as you can, tell us if these shapes are the same. And what that means is, can you rotate the one on the right some way or another so that it matches the one on the left, right? And here you can. If you take this one, you can imagine kind of rotating it like that, and it matches the one on the left, right? Here's a pair that don't match because they're mirror images of each other. You can't rotate this one in any way so that it matches the one on this side, right? So if what you really care about are the ones that do match, and you find this really cool relationship where the response time is just a linear function of how much the things are rotated with respect to one another, right? Which is kind of intuitive. The way that most people report doing this task in their head is they imagine rotating the one, right? And then seeing, does it match the other one? So if you barely have to rotate it, then it's not going to take you very long. If you have to really rotate it, some amount of time, then it's going to take you longer, right? And even if they're just the exact same image, it takes just a little bit of time to push the button and make a response, right? But Shepard and Metzler in the 70s argued that this provides evidence for the view that what we're doing in our heads with this is a kind of analog process. Why? Well, because if it were a digital process, if we did this the way computers did, we might do something like multiply it by a matrix, right? A rotation matrix. And if that's what you do, you'd expect this to be a flat line because it's going to take you the same amount of time. You just apply a matrix, right? It just happens in a certain number of steps. But that's not what we find. So it's like we have to kind of go through all of them, right? And importantly, for me, that's true whether or not we can really do that in some sense continuously, or if we can only do it in small, half-degree steps or something like that, right? Okay, so let me kind of wrap up here. The story here is analog computation is computation involving analog representation, what I said, right? And what I haven't really told you is what makes it computation. That's a bigger story. That's for another talk and the book and maybe later books or whatever. But let me hint at the general idea. Analog computation is going to be the manipulation of analog representations somehow or another. And you're going to have some kind of a mechanism that manipulates those representations. And there are going to have to be some constraints about the kind of manipulations that you do. The manipulations are going to have to be manipulations of the properties that matter for the thing being a representation, right? So for example, in my laptop here, there's a lot of digital representations doing lots of things. One way to manipulate them is for me to just, hold a hairdryer to it and heat them up. That's a manipulation, right? But that's not the right kind of manipulation because heat isn't the property doing the representation, right? There's a lot more to spell out here, but that's the general idea. And the cool thing about this, and this is another point that would need to be spelled out quite a bit, unlike digital representations, analog representation, and thus analog computation, it takes advantage of, rather than abstracting away from, the physicality of the representation, right? There's a lot more to say about this, but in a way, that makes analog computations not kind of medium independent in the way that digital representations are, because it's going to depend on what medium the analog representation is using. If you're doing it electronically, that's one thing. Mechanically, that's another, right? But I think this might well be the kind of computation that brains evolved to perform. like I said, that's sketchy. I've just given you a couple minor examples because the main point of this was just to let you all know what analog computation representation is about. But I think it's a promising line of making sense that, yeah, brains literally do compute. And yeah, it's not digital, right? But it could be analog. So to back up a little bit, for the story about understanding computation in general, I think this kind of dovetails well into a story about, well, what is computation generally? I think it's the mechanistic manipulation of representations, right? And again, where the manipulation has got to be the right kind of manipulation. But the cool thing is, plug in what kind of representation is being used, and you get what kind of computation is going on. If it's a mechanism that's manipulating analog representations, you've got analog computation. If it's digital representations, you've got digital computation. Oh, that should say representation, yeah. Oh well. Okay, that's the end of the story. Thanks so much for paying attention.
So we've got lots of time for questions. Do you want to just handle your own?
Sure, sure. Yes, Roy.
Okay, so the lovely talk. I really
Thank you.
enjoyed that. It's great stuff. And so I just want to focus on the notion of the algorithm.
Mm-hmm.
It's clear in Turing's sense that you have a set of inputs, set of outputs, and this notion that you have a set of states that you can go into, which will change your input-output mappings. But the way in which you systematically go from state to state, depending on the inputs and depending on the current state, is what we call a program. And you can represent algorithms that way.
Right.
So taking the notion of analog representations, which is fine, they're just as in the symbols in a symbolic computation, representations can be analogs. But the transformation from analog inputs to analog outputs, these systems can do that. They're really elegant machines. But what they don't have is the ability then to say, okay, now that I've performed this input-output mapping, now I should go into perform the next analog transformation. And depending on the output of that one, I should step into the next one. So if you had a system doing that, that would be computing on analog representations. But what is explicit about this form of computation is that there's a system program that's orchestrating things.
Right. So there's a couple of things to say about that. The one thing is to say, okay, well, is there something in the analog mechanistic story that is the analog of an algorithm, right? That's one thing you could say, and that's a possibility. I mean, I think this is a great question. I don't have a complete answer for it yet. The other thing to say is more of a philosopher's move is to say, okay, well, for one type of computation, what you need is algorithms, specifically symbolic computation or digital computation. For this other kind of computation, you don't, right? Because what's our concept of computation have to do with? Is it really the case that if you're moving, doing something with the slide rule, where you're not really following an algorithm, you're just using the mechanism, right? If that counts as a computation and that counts as an algorithm, then that's kind of the first thing to say. Say, well, if it doesn't count as an algorithm, then there's computation without algorithms. So algorithms are necessary for one type of computation. Something similar but not quite the same thing is necessary for a different type of computation, right?
But it still could involve a slide rule. There's many procedures in engineering that have you looking up on the table, transforming that value which was performed in an experiment and set the analog on the slide rule. But you would have a prescription for transferring this number up to that number. That's how it used to work with slide rules.
Right.
I did this in my undergrad days. You take that number and set it on the other scale.
Right, and then you move it to the right.
And then,
right.
And so that process is computation. It happens to be working on an analog representation, which is fine.
But insofar as that stuff is all an algorithm, you do that with an analog computer too, right? You set the input to the right value, right? You set the parameters of the various things, and then off it goes, right? Like with the slide rule, it's very different than, doing multiplication longhand, digit by digit, right? In the partial products way or whatever it's called.
Yeah,
right?
yeah.
Yeah. You had your hand up first, I think.
Thank you. Thank you for your interesting presentation. I'm not sure if I understand you right, but it seems to me that the analog computation does not really care about the physical mechanism of the brain, but it aims to develop some explanations of the representations of our mind functions. And if that is right, then I'm curious about how do you understand the distinction between the analog computation and folk psychology, because it seems to me that folk psychology and also psychoanalysts are also interested in how to explain our representation of the mental states. And they also have a lot of theories try to build models for our mental representations. But those theories are very far from what we are now talk about the philosophy of mind. So how do you understand this distinction?
So let me take the second part first. I don't know how much this would apply to levels at the kind of folk psychological level or, personal level or whatever. I don't know. My primary aim is to say, these neuroscientists say the brain is computing. What could they possibly mean? They definitely don't mean digital computing. Is there some other notion of computing, a principled notion of computing that could apply? And I think this is a possibility, right? To the first thing that you said, I'm not sure what you mean when you say that analog computation doesn't really care. I'm not sure exactly how you put it, but doesn't really care about the physical, what do you say, the physical
mechanism of the brain. So it does not talk about the neural mechanism and biological physical essence, but it talks about the representations of our mental function.
But those things go hand in hand. You can't talk about the representations without talking about the physical nature. I think that's what's unique about analog representations. So for example, when I talk about the stretch response on the muscle cells that Adrian did those experiments on, we very much have to care about the physical nature, namely the frequency of neural firing, right? The frequency is just what is the analog representation of the stimulus, right? So yeah, we do have to care about the physical nature. And if the physical nature was something else, then it would be a different kind of analog representation. If it was some other physical thing that was co-varying with the stimulus, right? Then it would be also an analog representation if the covariation is there, but it would have to be some other physical property you'd have to identify. Yeah.
But what do you mean by the physicality of the brain as you mentioned in the slides?
That, again, what makes an analog representation is the covariation between some physical property. You have to figure out what the physical property is, right? That is just what makes it analog. And so not every variation is going to covary in the right way. And not everything is going to be a representation, right? That's just what I mean. Yeah. I think, Vincente? Yes.
It's actually can be seen as a follow-up to the last comment.
Okay.
I was wondering about the notion of analog representation, because it seems like, as you said, that covariance itself doesn't count as a representation.
Yeah.
I mean, it seems like you need other things. And one thing, for example, in the example that you put the thermometer and the other stuff, there's kind of an interpretation relation there, right? The covariance between the increase in tall and the temperature is interpreted by us.
Right.
As a representation, right? And I think kind of the same thing can be said, or a similar addendum to the covariant itself is made by the normative claim that there are things that do represent.
Yeah.
There are things
Yep.
that don't. So can you tell us more how?
Yeah, so here's the Weasley answer, but it's honest. This is not a story of what a representation is. This is a story where I say, you give me a representation and I'll tell you if it's analog, right? Because as you mentioned, monotonic covariation is cheap, right? I mean, the temperature of the wall is monotonically, presumably, covarying with the temperature of the air, right? And I wouldn't call that a representation, right? The less Weasley thing to say is, there are reasons that we might postulate representations in various cases, right? And this is a complicated story, but I think an illustrative example is, my go-to example for this is, tree rings on a tree. We can use those as representations of the age of the tree, right? Is there any reason to think that the tree is representing years? Is there any mechanism in the tree that cares at all about age? Doesn't seem like it, right? There's a similar mechanism in, there's a variety of species of cicadas that emerge from the ground after a prime number of years have happened. Why primes? There's a story to tell about that minimizes overlap for different species, right? There's a counter, it's a different mechanism, but a similar thing is going on, like a layer of stuff is being added every year, right? When the layer of stuff gets the right number of years, cicada knows it's time to emerge, right? So is there reason to think that that's a representation for the cicada? Yeah, seems like a pretty simple counter, right? So, there are ways to say, well, yeah, it could be used by representation for someone else or whatever, for this kind of organism, for this other kind of organism. It seems like it's using that information, right? That it's natural to call that a representation, right? An analog representation, in fact, right? But yeah, again, I'm not saying for analog representation, all you need is monotonic covariation, because then, it's cheap and it's everywhere, and that's a bad result. Yeah. I'll try to go on one. I think he's next.
I'll keep as brief as possible. I kind of wanted to follow up something he said, but also something you said. Okay, so it seems to me like I'm trying to really conceptualize the exact barrier between analog representation and digital representation. The only thing I can think of is when you look at a computer, when it comes to, okay, so you basically have these, like a lot of the compute, like you have like an add unit or whatever, it's using binary arithmetic, and eventually you can combine those sorts of things together to add digits and stuff like that, right? And there's something, in a sense, in virtue of the representation of the like the way it's representing the digits, right? Where you can actually do this strange binary arithmetic to end up simulating, okay, like what you would do when you do the actual, you actually act out the algorithm or whatever. But at the same time, you could make the case that the way the computer is doing it isn't really, like, it has nothing to do with how you actually think about how adding would work. For instance, okay, there's two now instead of 1 and 1. It's not doing anything like counting. It's almost like it's just kind of moving things, and somehow that moving of things is actually covariating with that result. Like manipulating the direct representation of the thing is affecting that. And I'm also thinking about this in terms of like with the circuits that are underlying it as quotes. You can have memory circuits like NAND circuits are the ones where you only need NAND circuits, and you can build up basically the other kinds of logic circuits, you can build logic gates. But then you can also use like two of other ones. And so there's it's also an arbitrariness in which, okay, you say these things are continuous, but it doesn't matter which kind of circuit you're using, because there's a closed set of complete ones that use the NAND and then not and whatever. Like there's certain combinations of things. They'll end up giving you the result. Is that what you mean by the difference between analog and binary? I mean, analog and like more digital representation.
Yeah, so sorry, I didn't quite follow all of that.
They do two things at you.
Well, okay, so just take a binary representation of like 4, right? You have 1, 0, 0, right? And so that's in a computer normally represented by like, you've got a high voltage and a low voltage and a low voltage, right? and then add 1 to that, then you have high voltage, low voltage, high voltage, right? In that case, you've got a little bit more voltage, right? But the way that we do the arithmetic with that, it's not like we have just a line of voltages and we just add them up, right? Because sometimes, you know, you're going to go, if you go from like 7 to 8, right? You got low, high, 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 right? So you've got 3 voltages, right? Add 1 and you've got high, low, 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 right? Now you've got actually fewer voltages, less voltage, right? That's just the way that digital representations work when they're physically implemented, right? It's just different things, right? Different symbols. They're not actually bigger. But the analog representations, like the voltages in the electronic computers, like if you're representing 4, it's 4 volts. If you want to add more to that, the voltage just increases. It always does, right?
It's in that sense,
Yeah.
where black will be more volts, because it really has to go very, very smoothly along that.
It doesn't have to go smoothly, because like the example of the step function, right? It can jump around, but the voltage just is the value, right? Whereas you look at a digital representation, if you just measure the voltages, you don't know, you know, even if you knew it's in binary, it's like, well, which is the least significant digit? What's the most significant digit, right? You'd have to know that too, right? And different, probably know this.
It seems to be the sort of layer of interpretation of this, almost like there's a cognitive sort of layer that's added. And that could bring me back to tying it to what you said. It also seems like like what constitutes a representation is kind of relative to I'm always trying to say like a sensor or something like that. Some sort of parameter within like the way you think of these things in robotics, right? In terms of, well, this is doing like, you know, you can imagine like with a bat, for instance, you could think of a wall as being something like a representation of physical distance because of its echolocation, for instance, right?
Yeah, let me back up a second and say maybe another way to get at this is there are, by the way, a lot of people talk about the analog digital distinction as if they're mutually exclusive and, you know, that covers everything, and I think that's wrong. So digital representations are about representing the names of numbers in a conventional sense in which we can use the name of the number to calculate what its value is. Well, that was a lot to say, but, you know, 347, we all know what that means is 3 hundreds, 4 tens, 7 ones, and you add them, right? Analog representation of that same value would be, I don't know, pretend that's 347 centimeters or something, right? There's another way to represent the names of numbers. We only do this for particular kinds of numbers, but like, you know, pi and e, right? Where this doesn't tell you how to calculate the value of the number at all, right? So digital representations are a way of representing the names of numbers in a particular conventional way. Analog representations are just the quantities, right? Representing the quantities by some quantity, right? So that's another kind of succinct way to put the point. This is like super clear to me because I've been worrying about this for a while. So if that's not helpful to you, ignore it. But that's another way of kind of getting at it, right? I think you were next, Bill.
I think clearly there's important room. I mean, I'm thinking of things like perception and stuff, and even the stories about the nerves coming in the way that, I mean, there's a huge amount of analog stuff there that you really need to even get off the ground. But your question about this higher order pulling together, and are you, I guess, are you suggesting that if we don't do the kind of ignoring of analog that's you see all around in this stuff, we would have resources at this higher order level that could do the sort of, that could improve on the way improve, I'm maybe going to put it this way, improve on the limitations that come from the just looking at the digital.
Yeah. So let me mention one specific example of this, right? So there are some people that, I think this is a good thing to do. There's the whole field of computational complexity theory, right? Where we want to figure out how many steps generally does it take to perform some kind of algorithm, right? That's fantastic. But that only really applies to digital representations, right? For analog representations, analog computations, it depends on which medium you're using, right? So like the mechanical multipliers, it's instantaneous. Other things, like if you want to add numbers and you have, lengths, and you have to put another length here, and then you've got to measure the whole thing, it's not instantaneous, right? It depends on the physical medium. And computational complexity theory by design is meant to just abstract away from all the physical details, right? But you can't do that when it comes to analog computation and representation. And this is one of those areas where, it's kind of hand-wavy, but I think that neuroscientists already care about the physical nature of the representations, right? It's not to say that computational complexity theory is irrelevant to what's going on, but it is irrelevant to what's going on in analog computations, and that's what the brain's doing. Then you don't need to worry about the computational complexity of various kinds of algorithms, right? So, we might be missing an important way to think about computation and representation if we're limited to thinking about what computation and representation is. And the important part of this whole thing is this is all a principled way of thinking about computation. This is not just some ad hoc thing, right? It's just that we forgot about it. Yeah. Mike, I think you're next.
So you say monotonic covariation is true and ubiquitous.
Yeah.
Which may be true in a lot of places in nature. One place where it's probably not true is the nervous system.
Yeah.
That's good.
So if you just draw a Gaussian for me.
Sure.
So something like that is a typical tuning curve for neurons in the visual and motor system.
Right.
So if you've got, for instance, spike rate on the y-axis, and you've got a wavelength of light on the x-axis, that approximates the tuning curve of cone cells. If you've got angle of reach on the x-axis and spike rate on the y still, that's an approximate typical tuning curve for motor control neurons, say for limb nerves. That same thing, if it's angle of a stimulus, that's a typical tuning curve for edge-sensitive neurons.
Right.
The temperature sensing system is crazy complicated, right? All kinds of nonlinearities. It's definitely not monotonic covariation between temperature and the response of our temperature sensing system.
Right.
That depends not just on the relationship between your current temperature and the external temperature, but also the rate at which those things are changing.
Right.
Anyway, so I know you said this is the thing we know the least about so far.
Yeah.
But one way to put the question then is how limiting for your theory is the requirement for monotonicity if you do want to apply it to the brain?
Yeah, so tell me how much this makes sense, because I think this is a really good question. This is a hard question, right? So let's take something like, I hate this language of neurons preferring various things, but it's convenient, right? So so there's a neuron that prefers a certain, angle of the stimulus, right? And so, here's the preferred angle, right? What I have to say is something like, when we go outside the preferred angle, it's the absolute value, right? So if it's, 10 degrees one way, it's going to be this way, 10 degrees the other way, it's this way, but it's symmetric. So what it cares about is the absolute value, and that is monotonic, right? And so for all those examples you mentioned, I think I can say that story. But yeah, the neurons, they basically, so another way to put this is, if you just know at a point the neuron is spiking at a certain rate, you don't know if it's on this side or if it's on this side, right? So what it cares about is the absolute value of the distance between the preferred angle and the angle that it's getting, right?
That's fair. That's fair. It gets a little complicated though, because whether it's over there or over there, it's going to make a difference in the behavior.
Right. Which is going to then,
care about more than the absolute value.
Right.
So you have to have some kind of story then about if the representation is just a representation of the absolute value, how do you get the real value?
Yeah, and my hope is that you can put that story together by saying, okay, well, this neuron's doing this, and it's connected to this neuron this way, right? And there's various memories for things or whatever, right?
I mean, the classic story here is vector arithmetic, right?
Right.
And so the preferred thing does matter.
Right.
It's how much that preference is expressed. That's why the absolute value
Right.
there comes into play. But the representation isn't that. Right? The representation
Right.
is the vector.
Right. Okay. Right.
It's not analog.
Yeah. So, admittedly, these are hard cases for me.
Sure.
And so, part of this, I think this is a feature of this account, is I'm making some empirical claims here. If this is not what the brain does, and the brain is not an analog computer, and then we have some choices. We can abandon the claim that the brain is computing anything, because it's not any principled version of any computation that anyone knows about. Or you're going to have to come up with some non-ad hoc notion of computation, say the brain is a computer, and furthermore, the way it's computing is this way, and that's similar enough to these other kinds of computation, such that brain computation and analog computation and digital computation are all, species of computation in general. But I don't know how you do that, right? So, that could be a possibility too. Yeah. Michael.
Hey, thanks for the talk. So I wanted to follow up with more hard cases.
Oh, good.
Examples. So one thing I thought of, and I won't say too much about it, just other than to throw it out, is like how the brain solves certain problems like binding and like feature integration. So this seems to involve encodings, which aren't really like analogs of the thing out there. So for instance,
Yeah.
if binding's done via synchrony or something.
Yep.
But the more problematic case I had in mind is temporal encoding. So like in the perceptual system, basically you have non-synchronous inputs coming from synchronous outputs, like audio-visual things. And so somehow the brain has to register or encode that this auditory signal that's just a little bit behind this visual signal actually are coming from the same, they have the same source. And like, it's not clear, like, so presumably that encoding is like just some other neuron firing somewhere else. And it's just not clear to me how that kind of marking of temporal synchronicity is analog in your sense.
I have no idea. Yeah, that's a simple answer. I mean, what I'm, so there's something to say here, sort of, maybe. At a low level, this machine here is digital. If you want to understand fully how a computer works, including the circuitry, you have to understand digital representation and how those digital things are working, right? At a much higher level, it's really not digital at all, right? Like, I can move my finger on this thing and the cursor goes left and right? And at that high level of abstraction, you don't need to understand the numbers involved. Maybe the story that I'm telling about, how the neurons work, it's going to be, this is how we can understand it, some kind of low level, the kind of, not in Mars sense, but just the low level kind of hardware. What are the basic computations that are being performed? And then when we move up to larger neural ensembles or whatever, we can understand them in other kinds of ways, right? Clearly we do things that are not based on analog representations, like speaking sentences and things like that, right? But I mean, that's just a hypothesis. That's me waving my hands. I don't really know. There are other examples though, like, you can hear a sound over here, and you need to turn your head this way based on the time differences of, how the spikes get there. So those kind of more simple timing things, I mean, that's an analog representation. The difference in the spike times is that varies with, how far away the thing is and or the angle or whatever. So for simpler cases, the story maps nicely, but for the other cases, I honestly just don't know enough about that.
Just
Yeah.
So it's basically a suggestion. So
Sure.
I wonder, would you accept that the distinction between analog and the digital is task dependent? For example, like you use, for example, the brain use neural system to compute, but sometimes the neural signals, what represents is the firing rate of the neurons. But sometimes it is the specific spikes. For example, the
phase of the neural entrainment, you go together with some beep, and at that time, what it matters is the specific timing of the firing of the neuron. So I wonder, does it mean that in one case it is a digital computer, for example, when you are matching with the beat? In another case, maybe it's the how strong the light is, then it is the viral rate of the neuron encoding information that is analog.
So I don't know of any cases where the brain seriously uses digital representations, or neurons use digital representations. I don't think neurons ever represent numbers this way. I mean, this is why...
How about on and off?
On and off, so it might be using from... I'm not familiar with the second case that you mentioned, but it sounds like those would just be analog representations in different dimensions. So if it's, the distance, you've got the spike, and it's a distance in time from some other event, then it's analog with respect to time. Or in the case of frequency, it's, how many spikes there are, the frequency, right? I think. But I wouldn't call that second case digital. Like I said, people like to talk about this analog-digital dichotomy, and I think it's misleading. This is not a digital representation to me, it's just a symbolic representation. The brain may well do that too, right? Where it's just a certain pattern of neurons firing arbitrarily represents something else, and you change the pattern a little bit and it arbitrarily represents something else, just like words, right? You can change one letter of a word and it just arbitrarily represents something completely different, right? There's no kind of similarity when you shape up the actual representation. So, sorry, that might have been a little bit too much in one answer. But, yes.
Yeah, thanks very much. Have you looked at or thought about was a friend Dratsky's work on this?
Yeah.
Yeah, and especially, maybe you don't need to answer the question, but I mean, he at least had a story about where covariation actually becomes representation, and that's this ideological story about being co-opted precisely because it has the covariation that it does, and the creature can exploit that covariation.
Yeah, and I'm sympathetic to that story. I think, I haven't studied the details enough of what exactly he has to say because, like I said, it's division of labor in philosophy. I'll let other people come up with the theory of representation generally. I mean, that's a hard enough problem. Yeah. And then I can come up with a count of, specific types of representation. Something like that, for me, more or less has to be right. But this stuff is difficult because Dratsky uses an analog-digital dichotomy in a way that I think is not helpful, right? And so it's a bit of a problem for the overall project when I would be a purist and say no, analog and digital mean these things and stomp my feet and you have to use it this way to understand what's going on. Whereas, people who are much more established and read like Dratsky, should I just go with what they say? But anyway, yeah, the answer to the question is yes. I think that kind of story would be helpful, but that's not my primary aim. Yeah, right.
I want to offer you an example of analog computation. And I'll tell the story, but then the question will be to ask you what you think of this characterization of analog computation. So it goes back to good old Euclid of Alexandria. Euclid's algorithm is an analog. If you want to tile a room, you want to find the largest square tile that you can use to tile it evenly, so you don't have to cut any tiles. And so Euclid's algorithm was to measure the room with two dowels. You take the length and the width. So now you have two analog representations of the length and width of the room. And you can scale them if you want. It's immaterial. But then the algorithm proceeds as follows. You take the two dowels and you want to take those two numbers and successively subtract them. So in my hardware software co-design course next week, I'll be doing this. I write a C program for this. I build a piece of hardware to do this. But the fun thing is when I get up in front of them with the dowels. And so to subtract these two numbers, you hold them side by side, the same bottom, and then you snip off the top. And the part that snips off is the subtraction of those two
Yeah,
numbers.
yeah.
And now you need to successfully do that. So you take that number and you stack it up against either of the other two. You can throw one away. You stack them up and you snip them. So that's this, and then
Yeah,
you
yeah.
continue until what you've got is the two dowels are the same.
Right.
And that's the greatest common divisor of those rooms.
Right.
So we have no problem. That's an analog those are analog representations. But what I'm suggesting is the notion of analog computation is you followed an algorithm in order to do that. You followed a set of steps on analog representation, and that's that may be the characterization of analog computing. If you want to use the word computing here,
Right.
then that's a simple characterization.
That's a good example.
I'll offer that up.
Yeah, thank you. Yeah, I have another example that's another one of my kind of go-to examples of, we've got a little bit of time, so I'll go through this really quickly. It's a better example than the one that I just came up with. Let's get this part. So if you want to sort some numbers and you start off with a stack of cards and you have digital representation of the numbers on each card and you want to find the maximum in the stack, right? The simplest way to do this is you go through one by one and you keep track of the biggest so far, right? So go through them all. So what's the biggest one? 971, right? How many steps does that take? How many cards do you have, right? So it's big O of n. If you start with a bunch of analog representations, so this is actually from A.K. Dewdney and an old example in Scientific American, where he said, like, imagine you have a bunch of uncooked spaghetti noodles, right? And the height of the noodles is the number being represented. How do you find the largest? Well, you just take them and go like that, right? And just pull it out, right? So it's like a one-step kind of algorithm, right? It's an illustration of like, well, if you start with this kind of analog representation, then you can do this kind of task in one step. But yeah, I like your example too. That's a nice, like, oh yeah, that is a kind of more clear algorithm.
I mean, that's an operation on a data.
Yeah.
The thing about my example is that it's the algorithm that's the computation.
Right. Yeah, I like that. I'll use that and I'll give you credit. Other questions? Yes.
Chomsky uses the term digital in reference to linguistic computations. I'm not sure exactly what sense he uses it in, but is it a challenge to anything you have to say here?
No, so in passing, I mentioned this 2011 paper I have, where the title of the paper is Analog and Digital, Continuous and Discrete. And Chomsky and Dretske and other people basically take digital and discrete to be synonymous. I think that's a mistake when you actually care about computation, because discrete just means not continuous, right? These are discrete symbols, but they're not digital. This is digital, also has discrete elements, right? The reason it's digital, according to me and according to the way you understand this in computer science, we have numerals, and the numerals are in places, and depending on what place it's in, the numeral has a different interpretation, right? The cool thing about representing numbers this way is you can do a lot of nice algorithms with them, and you get a lot of precision, right? There's a most significant place, there's a least significant place, right? But Chomsky and other people who just say digital and discrete are synonymous, what they mean is, you take a word like bed, and it has, discrete elements. You can change one letter, you get a different word, right? But the thing is, there's no least significant or most significant digit here. I mean, there are no digits, right? Because there are no numerals. If you know what 3 and 4 and 7 mean, and you know what the places mean, this is the name of a number that specifies the value of the number, right? And you know the base and everything like that. Knowing the individual letters here doesn't tell you anything about the meaning, right? It's just an arbitrary, discrete, symbolic representation, much like these are discrete symbolic representations. So what Chomsky and a lot of other people mean by digital is, unfortunately, it's an unfortunate synonymous thing that people, I think, it'd be better if we had paid attention to that distinction, right? But so it goes.
I could be wrong about this because I read about this a very long time ago.
Uh-huh.
But I think there are physical systems that you cannot, this is going to sound implausible when I just say it, but that you cannot represent through, so you can't represent the process via a Turing machine computation at all.
Mhm.
But I'm pretty certain that you could represent that process through an analog representation, and I think the first paper written about this was in 1980 by Forel and Richards.
Yeah,
Oh, you know about it?
I do.
Yeah, good. So yeah, so when you first gave the definition of, or when you clarified the definition of analog computation via step function, so that's when I understood the definition. I wondered how you would be able to even tell whether a specific process in the brain, I mean, it seems obvious to me that they'd be analog computations, but how you could kind of prove that looking at it in terms of analog computations was more plausible than saying something, there was a digital computation, but then you gave your example of the time it takes for people to do the rotation thing, so that was a fantastic example. But if so these processes are very rare, like the Forel and Richards example, type processes are very rare. But if there are things like that where we're able to deduce something on the basis of the final physical state of one of these physical systems, where final can be almost any time actually, when you look at these examples, and react in a certain way on the basis of our representation of what we think this process is doing or is going to do, that would be a really great example to show that definitely analog processing has to be what's going on in our brain. But those examples are where you probably wouldn't find one, but if you did, that would be.
There's a really hard methodological problem here. Let's see if I can try to do it justice. Everything we know about brains, we measure things, right? I don't know what it would mean to say we know. Okay, let me back up. A very simple example of something a Turing machine cannot do, in principle, is a simple function defined on the real numbers. Like, a simple function defined on the real numbers, like y equals 3x, right? Can't do it. You can approximate it to whatever precision you want, but just generally can't do it, right? Do brains do that? Well, we can only ever measure things to a certain precision, right? Now, other physical systems in the world, we think, this is going to sound a little loose, but we think that the orbits of planets and certain things in physics, they really do use the number pi, not just an approximation to pi, but pi is really in the system somehow, right? Because if it's some approximation to pi, it falls apart, right? When are we licensed to say things like that in neural systems? I don't know, right? Because we're always measuring them, right? So that's one issue.
Yeah,
right?
That's actually the reason I almost didn't give this example. So the only way that it would work actually is if you need to know whether the value of a certain physical parameter existed within a certain specific range. Because then, if you did the analog computation, basically you would know right away whether it was within the range. Whereas with the digital computation, you wouldn't know right away. It would be a different, computability class maybe. But
depending on the physical stuff that's happening, that defines the candidate analog representation process. Yeah, exactly. Yeah.
So we're going to leave it there.
Oh, I
Please
see.
join me in thanking
Thanks.